So you'll have your bromide ion plus water. Both of these are going to make stuff. So sodium hydroxide and H+, and then hydrobromic acid and a hydroxide, right? So here you could say here, just based off the fact that you start off with 0.0064 molar for both of these ions, it's going to then create equal molarities of both of these ions. So therefore you could say, okay, equal quantities of those would yield a neutral pH. Or you could go further, which I think is a more advanced answer, and say these are both going to be reactions that don't occur as is, because that's a lie and that's a lie. Why? They redissociate again. Like, they will never exist as sodium hydroxide like pure and hydrobromic acid pure, because they're strong acids and bases. So they're going to revert back and reform these two individual ions in water. And then the real true answer is water has equal quantities of hydronium and hydroxide because of its autoionization. I think that's the more advanced answer, but I'm fine to take multiple answers like that, okay? Like, I give you credit for anything like that because you understand what I'm getting to. So I like this one because you say revert back, and then the water is going to be the compound controlling the pH, and the way it controls the pH is through autoionization, creation of equal quantities of hydronium and hydroxide. And then the last trace are 6 is, okay, so you had to do your salt hydrolysis here. Which was the weak ion you were working with? NH4 plus. And that's a little bit of a misnomer for me to say weak ion, because actually it's a strong conjugate acid. NH4 plus, right? It's a strong conjugate acid, but I say weak because I want you to know that's coming from that weak base. So anyway, it adds water. You do your Ka from Kb, solve, get your hydronium ion, and you get pH to be 5.827. Is also weak. This one's really similar to what you're doing in your lab anyway. So the weak counterpart would be the nitrite. So that's a strong what? Conjugate. Yeah. It's adding to, yeah. Strong conjugate base. So then you get your pH after you go through your find Kb from Ka to be 7.13. And 8 was weak and weak. So which one was bigger? Right, Ka for that one, for the ammonium equaled the Kb of acetate, right?
Yes.
And so then therefore they were neutral. Questions? Yeah.
So if we did one like that where the K and the Kb are equal, is that always the K and Kb and then they're neutral?
No, well, you would have probably done some work prior to that to like at least express to me how you even got to that point. Like, you would have written down the ammonium ionization, plus water.
Yeah.
You'd have written down the acetate.
So like after that point, is that all we have to do?
As long as you showed me that you've solved for the Ks.
Okay.
As long as you show me that you solved for them from the Kw over the Kb and then the Kw over the Ka. Yes, I'm good with that.
Okay.
Yeah. It's just like, if you really understand how to justify your work, then you'll get all your points, like all the time. Assuming sometimes you know what it does. So we gotta be careful with our assumptions. All right, Polyprotic, can we do this? Keep your reading guide on your desk. Keep this 8 problems on your desk, and if you started the equation writing, keep it there. I'll answer some of those questions in a wee bit. Okay, so give me an example of a polyprotic acid, anybody.
What?
I don't know the formula off the top of my head. Phosphoric acid. Okay, keep going. Give me it. Okay, so this one right here, what kind of polyprotic acid is phosphoric? Mono, di, tri. Triprotic acid, because it has 3 ionizable H's, or 3 acidic H's. 3 uri. Okay. Diprotic acid, sulfuric acid. There's other triprotics and diprotics, but I'm just going to stick to that. I think you get tri means 3, di means 2. So, most of the time whenever you're doing these kinds of problems, you'll be asked 2 things. To find the pH, which is not bad, and then find the ion concentration of every ion in solution. Okay? Every ion in solution means you've got to go through multiple deprotonizations. like sometimes 3 different reactions. And the first deprotonization is the only significant contribution to the pH. The only one that's significant enough to allow for pH to change drastically. So what are the successive deprotonizations of sulfuric acid? So I'll start. Sulfuric acid makes H plus and hydrogen sulfate, KK. And I'm gonna write this with a hydronium because you'll see it like this too, and I want you to be comfortable with it. There we go. All right, you see that my arrow here is a forward-facing arrow. Why?
It's a weak acid.
What's a weak acid?
It's a strong.
That's a strong acid. That is the only reason I'm writing this is because this is a strong acid. That's one of your 6 strongs, yeah? Otherwise, if it were weak, which this next thing that I'm going to ionize will be weak, so we will be doing double-headed arrows. So that's the first deprotonization. Then I take this guy, that conjugate base that was made, and I make it act like an acid. I make it deprotonate. So hydrogen sulfate plus water yields what? I'm sorry, not yields. Equilibrates to what? Plus SO4. And I can't go any farther. 2s. Because I don't have any more. So diprotics will have 2 BCs, triprotics will have 3. Monoprotics will have 1. Makes sense. And so sometimes you'll have to draw these or look at it via a diagram like this. So this right here from sulfuric acid to hydrogen sulfate here, that double-headed arrow is actually a little bit of a lie because usually it does not go back. Because that is less. One of these bonds here are weak, and so one of them will allow for deprotonation to occur. This can go back and forth though. Okay, now each of these values will have their own K value, and you probably saw that in your reading. This is Ka1 and this is Ka2. And what does the Ka stand for again? Like, what are the words that go with that? Okay, acid dissociation. Thank you. So if I ask for you to find the acid dissociation constant, don't think of like I'm speaking gibberish to you. It just means sulfur Ka. Or I might say find the first acid dissociation or the second acid dissociation just to verify Ka1, Ka2. Cool? Yeah. So,
Attention teachers, the EVOS training will begin at 1 o'clock for any teachers that will need it. It will be held in the upstairs workroom. Thank you.
yes,
So
ma'am.
to get the K1 expression, you use the first.
Yes. Thank you for saying that because I didn't actually say it. And I'm assuming, you know. So, yeah, you take these products over this reactant for your Ka1, and then these products over this reactant for Ka2. Okay? And generally, almost all the time, it will successively get smaller and smaller and smaller and smaller. So the Ka1 will always be greater than Ka2. The reason why is because once that first deprotonization has occurred, you already got some ions in solution. You just already have H pluses in solution. So it's acting like a common ion effect because when you already have H pluses or hydroniums in solution and you go to the second deprotonization, you already have some of this guy in solution. So it's actually acting like you're shifting back to the left, so then the Ka value is smaller because you're not going to even have the possibility to make nearly as many products as you did the first time. Yeah?
Is that what we were doing yesterday with the water that we were adding?
No, you were diluting it via a serial dilution. I just wanted to show you how to do a serial dilution. So when I got to college, I didn't know how to do it, and I was like, I had to ask somebody, and they thought it was real dumb. Yeah. So I was very poorly prepared for labs in college. You guys would be like, I'll pay you pay me money and I'll teach you how to do this. Use your strengths. And yeah, I think that's all I'll tell you. I will just note that remember anions yesterday? Anions, are they fond of losing protons? No, they'd rather hold on to it because of that negative attraction they have for that proton. So it's a little harder to deprotonate this one than it is to deprotonate that neutral one, due to the fact that it now has a negative charge overall, so it's holding onto its positive charges, aka its protons, its H pluses, and so you're going to make less and less products as you get more and more negative. So if I could make this like H SO4 2 minus, that's not true, but if I did, that would even be harder, so it would have a smaller Ka value. So let's do some problems like this. Let's calculate, and this one I think is the one that's on your packet. Is it 5.0?
Yes.
Okay. Okay, so phosphoric acid, equilibrium constant. I want all the equilibrium concentrations for 1, 2, 3, 4, okay? And then I want to get the pH as well. So I'm going to start off with the first deprotonization. I have to write in different colors on this. I recommend if you have a highlighter or a pen or something to kind of like segment your work throughout it. So the first deprotonization is phosphoric acid doing its thing. I'm dropping off some hydrogens in the pool. H2PO 4 1 minus. We have this book today. They missed that AP. Okay, go to the first one.
Yes.
What's up?
I think you have a typo, like, okay, so there's like a phosphate ion and then one left.
There's an imaginary 2 right there. Is that what you're saying?
Sorry. That's what I was saying.
Yeah. Sorry. There you go. The imaginary 2s. I try to imagine them, they don't get up here. Okay, so the Ka value is established for us. You can see that it has 7.5 times 10 to the negative 3. I'm going to run through like 1 or 2 of these problems, and once you get it, please let me know, because these go on forever. Questions so far? Q&A? So 5.0 molar, don't care about water, 0 and 0. Minus X, you're just iceboxing, like, for days here. And I'm not going to write an ice box on all these, I'm going to write an ice, like, word. Yeah.
So, like, on our test, is it okay if we just jump straight, like, we wrote out the equation and we just show you E, like, we
Yes,
like atoms?
please, yes. Okay, so I always try to do the first one fully out, so everybody has one full example. Because I've had an honors homework before where I skip steps and they come back to me like, I don't know how you got from A to Z. I'm like, oh my gosh, I'm sorry. So I want to make sure you're okay. All right, so the Ka1 expression is hydronium, H2PO4 1 minus over phosphoric acid, which equals that thing right here. Therefore, we have x squared over 5.0 minus x. What do you guys want to try to do with that x? Neglect. This is where my different colors come in, because I need to remind myself I need to prove that it's okay to neglect x. I have these calculations over there. I'll find them. X squared over 5.0 is equal to 7.5 times 10 to the negative trace. Blah. Okay. And then when you solve for x, and you know, I said up here, x is now equal to my H plus and my that thing, H2PO4 1 minus, and that equals 0.1936. Yeah? Okay. And I'm just extending my decimals around because I don't want to have rounding error. Okay. So we can go right now, we can try to find the pH. Okay, let's go ahead and find the pH. And I notice that I do already have my 2 ions established. So I'm just going to leave those there, try to box them off so you understand what you have written down. pH from this acid is negative log of the hydronium. And the only reason I'm going straight here is because the first deprotonization yields the most H pluses. The next ones yield successively much smaller, and they're not going to be significantly impacting the pH. So plug, plug, plug. What'd you get, Tara?
0.712, so
0.72 pH. Okay. All right. Now the next deprotonization is occurring, of course, after every single phosphoric acid is gone. After every single one of these has deprotonated. That's going to anyway. We're going to form only this in solution. So now we have only H2PO4 1 minus to work with for the second deprotonization. And we have a starting point with this. We already have some of it in solution, and we have to identify that. How much do we have in solution? X's amount, which is 0.1936, right? Plus water. So this is my second deprotonization box that I'm going to kind of sketch up here. Equilibrates to hydronium plus HTO4 2 minus. And then I have, the water doesn't matter. Do I have H pluses in solution already? Yeah, I do. So I have to start with my icebox here. with an initial amount of 0.1936 for my hydronium, but then I have 0 left of, or 0 original of the hydrogen phosphate, diphosphate. Now minus X plus X plus X, and that's going to be my equilibrium. I'm just going to kind of like red like that, like that's the equilibrium now. And then Ka2 is equal to hydronium times HPO4 over H2PO4 1 minus. Plug, plug, plug. So 0.1936 plus X times X over 0.1936 minus X. What are you guys going to do with those X's? Neglect them. And notice that they neglect top and bottom. Only the ones that you're adding and subtracting are the ones that you're allowed to neglect. So what do you guys want? That's pretty easy. Like, I don't even have to do much more work. I set it equal to Ka2, which was, you can't see this. Ka2 is up on the top of the board. 6.2 times 10 to the negative 8. 6.2 times 10 to the negative 8. What have I just solved for? Say again, Grace? X, because you see that 0.1936 cancels on top and bottom as well after I've neglected the X's. Yes? So I've actually solved for X. X is equal to the Ka2 value just because of how the math worked out. It's not magic, it's math. All right, what also have I, well, no, what else, no, I'm sorry, X equals in this case the HPO4 2 minus, right? So I have to kind of note that value. And that's concentration, which is molar. Notice since that X is so tiny, X is 6.2 times 10 to the negative 8, if this is my original amount right here of my hydronium, 0.1936, that little tiny bit is not going to do anything to the pH. So my pH, even if you try it, you take that 1.1936 and you add that little bit of X, and then you recalculate pH, it's not going to change it. So I already know it's not going to change it, so I'm not going to do it. Yeah.
What number should we how small should the number be?
Usually when it's off, when it's different by 3 decimals. Like this is 1.9 times 10 to the 1.936 times 10 to the negative 1. That's 10 to the negative 8th. Big gap. Yeah. Yes, that second one, because the second one, the Ka value, good point. I mentioned say this earlier when I had that example up. The second Ka value for sulfuric acid is like 1.2 times 10 to the negative 2. This Ka value for 2 is 6.2 times 10 to the negative 8. So that second one for the Ka value of sulfuric is actually significantly important because it will contribute a significant amount of H pluses. But you can try it and you would see it too. Okay, so then we have this one. Let's do our third and final deprotonization. And we're going to take HPO4 2 minus plus H2O equilibrates to phosphate and hydronium. You start off with a specific amount of this already, 6.2 times 10 to the negative 8. You start off with a little bit of the hydronium. And so if I do add that 6.2 times 10 to the negative 8, it's not going to change that number, so I'm not going to change that number. Like, that's so far apart in terms of decimals, I'm not going to stretch it out to that many sigfigs. So I'm going to subtract X over here, add X over here, and add X over here. So I just kind of went straight to E here, as Tara suggested. My Ka3 value is equal to hydronium times phosphate over HPO4 2 minus. This one, the math, you do have to do a little bit more math here. It's not like quadratic or anything, but you have to divide and multiply. Oh darn. 6.2 times 10 to the negative 8 minus X. What do you want to do with X? Neglect. And then set it equal to the Ka3 value. which is 4.8 times 10 to the negative 13. So yeah, we're pretty good, pretty far away here. So you can see that it's it's a lot lower than the Ka 1 and 2. All right, and then X, once you've, when you take your 4.8 times 10 to the negative 13 times your 6.2 times 10 to the negative 8, divide by your 0.9 or 1936, math is what I just said. X is equal to, when you do that math, 4 minus your phosphate, which is X, is equal to 1.537 times 10 to the negative 19. So do you think it was okay for us to neglect X? Probably. Because 10 to the negative 8 over, 10 to the negative 19 over blah, 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 10 to the negative 8 times 100 is going to be less than 5%. Way less, like extremely less. Like I don't have that number, but it's really small. Okay. There you go. That's all of the ion concentrations. The only other one that you will sometimes be asked to do also, in addition to all of these ions, is to do the other ion that's always in solution. Water would auto-ionize to what and what? Right. The OH minus is the only one we've not calculated. So how would you get OH minus knowing H plus? That would be way too hard. How about you just do the easy one, which is the KW one, right? 1.00 times 10 to the negative 14 is equal to H plus times OH minus. So if you had your H plus, you divide. So OH minus is just 1.00 times 10 to the negative 14 divided by 0.1936. Yes? This is a formula here. You should know because that's an easy one-stepper. I don't know what that is because I didn't calculate it though on this one. All right, so that is polyprotic acids. They're just long. They're just a bunch of ice boxes, and then you making sure you calculate and plugging in whatever was formed previously in the next ice box. Yes.
Is there any way to like check that you got the right pH from like the other things?
Yeah, because you could add your X's that you accumulate here, and you could re-plug it into pH, and you should be getting the same number. Yeah, you should be. If you want to get it right. All right, questions here. Yeah.
When you're neglecting X, when do you have to like prove that X is neglectable? Is it at the beginning?
On this
step?
one,
Mm-hmm.
you should do it every time.
Okay.
You should. I'm not going to take off every time. If you show me once, I'm usually good with that. But I should on the first one that I neglect. Please try that because that's going to be the more significant of them because that's when X is largest. So up here, X is 0.1936 divided by 5 times 100 is, what is it?
I think I got 3.8% or something like that.
Yeah, I got it right here too. So X is okay to neglect because it was 3.87%. And then from there it gets smaller. So at least do it once for me someplace and then at least remind me that you still know how to do it. And you're kind of watching yourself. All right, I have one more thing I want to tell you here. On this one, sulfuric acid is the special one where your second deprotonization will be significant. Only because your first one, your Ka1 for sulfuric acid, it doesn't have a number. Like in the textbook, it just says huge. Okay? Because it's 100% dissociation. So like you're going to have 100% of the products over 0 reactants, which is infinity, right?
I was wondering when I put it online. I was like,
Yeah.
going. I just said huge.
It said large.
It's
Yeah,
just,
I was
it's
like,
very
that's
large.
a number. And
Yeah.
then I looked at nitric acid, it said about 20. I'm just like, that's
Yeah,
not
it's
helpful
just
at all.
huge because you can't even establish a Ka value because you have 100% products and 0 reactants left. You know, divide something by 0 doesn't exist. But the second Ka value is kind of significant, so you know that's not that small. I mean, 0.012, it's going to yield a significant X value, so therefore you should include it in your pH calculation. You just sum up your H plus or your H plus. Okay. All right, now I'm going to show you there's a chart in your packet. It's got like 15 equations, and I'm going to show you how to manipulate equations.
Which packet?
The printed packet that I printed for you.
Did you guys?
You can find it first.
It starts like this.
First
These that you have to use like you had a formula for.
I saw
I
that.
was like,
Oh, the quadratic.
yeah, is it on your
Oh.
exam?
They tried. Now that was like a couple years ago. They tried that too.
Look at it off.
I was like, praise Jesus.
There was one
Okay.
I wrote a note on. I forgot where it was.
Not lovely.
You guys find it? Okay. It's just titled AP Chemistry Polyprotic Acids. This is your problem set. I'm going to do almost all of it. You guys are going to do number 1. Okay? You're going to do number 1 after I finish, but I'm going to do this for you first. I'll list a couple of them, and then you guys can complete them with me. Okay, so your problem set plus a couple other like little catch-up things are what you're going to do tonight. All right, so here is, oh, I have to tell you how to do this. All right, so this one. Huh? I'll give you two. You're good. So the very first thing I just had pulled up here, the carbonic acid, that's what you are doing for homework. Okay, and then I have like 2 more on the next page. I'll show you that, but you'll finish it in class. That shouldn't be a problem. Okay, so you are going to have to identify how to manipulate K's from a variety of equations. Normally you just say, oh, well, if you reverse an equation, what do you do to K?
1 over K.
1 over K, you invert it, right? So K to the negative 1. If you multiply K by 2, then you're going to raise K to the 2nd power, right? So now you can manipulate them very similarly, but now that we have KAs and KBs, you know that I've been saying, find the KA from KB, or find the KB from KA. And when I say to do that, how are you calculating it? You use KW and you find the other one, right? So you've got different tools now. And then, now that we have KA1s and KA2s, you sometimes will have to specify, when you say KA, are you talking about KA1 or KA2? So you have to look at the whole equation to figure out which KA you're talking about. Pretty much you're just saying, am I dealing with the first deprotonization, or the second one, or the third one? So looking at this first equation, what 2 things stick out to you? So the carbonate and the bicarbonate, right? Is that a second deprotonization or a first deprotonization? This is a second one. It's just the pairing that's the second. So and notice all these are carbonic acid except for like this one. So carbonic acid will be H2CO3 and HCO3 1 minus. That will be the Ka1 of it, yeah? That pairing of ions. I know that's not an ion, but I'm going to say ion, okay? And then the second pairing will be carbonate or bicarbonate and then carbonate. And that will be a Ka2 related equation, okay? So you need to look first and see what you're dealing with. And here's my kind of go step-by-step process. 1, find water. Okay, figure out where water is. Is it on the left or the right? Reactants or products? In this case, water is a product. So that means my reaction has been reversed. Because I don't know if you've noticed this, but every time we do a acid dissociation or a base dissociation, it's interacting with water. Okay? If you put water as a product, it's because you've reversed that reaction. So in my head, if I found water and it's a reactant, I'm good. I'm not going to change up the K. I'm not going to manipulate the K. Hold on. Let me finish polyprotic acids. I'm videoing right now too, so, you know. It's one of my first babies. She made it through AP Chemistry. My first time teaching it, and made a 5. Blew it out of the water. So, where was I at? If it's a product, you have to reverse it. Okay, you have to put it over. Okay, and that's just because water is the one that is driving this kind of dissociation. All right, so when you find water, second step, find water, see what kind of ionization is occurring. Is it a base dissociation or an acid dissociation? Based on how it interacts with water. Okay, so how is this one interacting with water? Look at what forms when you go back. Acting as an acid or a base? You see how this deprotonates to water to form this? Going backwards, okay? You're focusing on water, and you see how is this ion interacting? It's acting as a acid. I have a different first one than you guys.
Yeah, that's like part B.
Oh, I must have skipped a page because I was like, I have the acid base on here. Let me just skip down. It's good. Okay, so this is acting as an acid. So act as acid. Just remember that, okay? So that means you're going to be using Ka, essentially is what I mean by that. Is this the first or second deprotonization? We just said this? Second. All right, so you're talking about the second depronization. So you're using Ka2, and since this reaction, that reaction is reversed, you do 1 over Ka2. So essentially you're finding 3 pieces of information, you're putting it into a Ka value, or a K value. So find water, figure out how this ion is interacting with it. If water is a product, that means this thing has been reversed. It's because it's the dissociation that's been reversed. This ion is acting as an acid because it's donating it to form hydronium and leaving carbonate. So it's acting as acid, so you're good to keep your Ka. And then it's doing the second deprotonization, so it's the Ka2. Let's do a couple more together. All right, so you can write this as Ka2 on the bottom or just Ka2 to -1. Just depends on how you can write it. Yes, ma'am.
And that's what,
That for me is fine to write there, but if it says to calculate it, you would actually literally go find the Ka2 value and actually plug it in mathematically. I'm fine to leave it just variable like, but if it says calculate, you're going to calculate. Yeah. Yeah, I'm fine with that because I know you guys, like, if you can plug in your calculator right, we're good. I trust that you can do that. Okay, so now where's water? It's a product. How is this guy interacting? I'm sorry.
It's a base.
Okay, water is donating, right? So this is acting as a base, right? All right, so I already know I have to find the Kb of a Ka, right? Now, what Ka am I dealing with? First or second? First, because I see the full version of carbonic acid, and then I see the bicarbonate. So I see that pairing that yields Ka1. So I'm going to find the Kb1 of Ka1. And now notice that this is a reverse reaction because the water is a product. So how do I want to write my K? 1 over Kb1. But that sometimes we're not sure what Kb you're talking about. So you could actually tell me Kw. This is number, okay. So like, how would you find Kb? You would find Kb over Ka1, right? And it's reversed, right? So then flip that around. That's the same thing as writing what? Right, inverting it. That's the same thing. Yeah, that's the same thing. So like, don't get stuck with one way of writing it because sometimes you'll see answer choices differently. You could see it as 1 over Kb1, which is really rare because there is no Kb for carbonic acid. You have to find it. So they try to not like identify as like a standard because that's not standard. It's an acid. So Kw over Ka1 will give you Kb1, but then that's inversed because it's reversed. Okay, this one I'm gonna skip for a second. Let's go down to another type like this. Find water. Yay, it's a reactant. So it's forward, so no flipping, no inversing. Okay. How is this interacting with water? It's donating. Sorry, I kind of told you that. It's donating, so it's acting as an acid. All right, so we have to find Ka. Oh, wait, we have Ka. Is this Ka1 or Ka2? Because it's the pairing of the first deprotonization. Okay, Ka1. That one wasn't hard at all. That's literally the Ka1 dissociation balanced chemical equation. Yeah? Okay, let's do one more and then you guys can work on this. Oh, where's water? It's a reactant. Okay. This carbonate is acting as a base, yeah? Because you see the water is donating to it to make the bicarbonate. Yeah. So we find the of Ka2. So I write that phrase out to myself, so that tells me to do what now? So negative? No, it's not reversed, right? Because water is a reactant. So this is the correctly written as a dissociation. That equals Kb2. And if you had to plug in values, you could plug in values and you could calculate. Hold on, I'm coming. All right, you guys, I'm coming. You guys finish A through I. You guys have to go. Hold on, I have to give Aaliyah a hug too. I have to stop recording.
Oh, hey.
Aaliyah. Okay, pop.